if another question comes up. But now I want to go on and talk about some features of endomorphisms and quantities that you can compute in quantum mechanics or observe in quantum mechanics. So this will have slightly less handholding, but still a little bit. All right, so we already know how to construct the endomorphisms of a vector space, or more generally an abelian group. If you've studied algebra, you probably know the endomorphisms of any abelian group form a ring. In this case, they'll actually end up forming not just a ring, but an algebra. But we'll get to that in a moment. So first, let's just think of endomorphisms from H2 itself. So H is a vector space, and the more pedestrian way of thinking of an endomorphism is just a linear map. So what is a linear map? It's a guy O that eats a linear combination of vectors, and it just commutes with scalar multiplication and addition. So the A1 comes out, and there's O on ket V1, and the A2 comes out, and it's O on ket V2. That's an endomorphism. Now again, my nod to the infinite dimensional case is the following, that in infinite dimensions, you normally have to restrict attention to bounded maps. But in the finite dimensional case where H is Cn, every linear map is bounded, and in particular, the number that bounds it is just its largest eigenvalue. So all linear maps are bounded. So we don't have to think about that. So for us, any linear map or any endomorphism can be represented as a matrix. So it's a matrix where the columns are the images of the basis vectors under the linear map in question. So if O is a linear map from C2 to C2, it can be written as a matrix with entries Oij, if you like. And for that reason, we're going to use some terms interchangeably. I'll say linear map, operator, endomorphism, and even matrix, and I'll use those all interchangeably for elements of this ring, this endomorphism ring, really algebra. Okay, so now I have to introduce a little more notation. So how do physicists tend to write endomorphisms or linear maps? Well, first, let's look at this. So I have not defined what it means to write a ket next to a bra like this. So since I have not yet defined it, I'll call it a formal expression. So here's a formal expression of an element of H written next to an element of H star. What is this object? Well, I claim it is natural to interpret this object as a linear map, an endomorphism from H to H. Why is this a linear map? Well, let's just follow our instincts. I'll take an element X in H, and then I'll write this mysterious object that we have not yet defined. So I write that in parentheses here, and then I write this element X of H next to it. Now we just follow our instincts. Well, what is our instinct? W is an element of the dual space, so he's hungry. This is some guy who's ready. He's ready to latch onto an element of H and eat him and give you a number. So let's let him do that. We let W run wild. So W latches onto X and eats him and gives me a number Z in the field of the complex numbers. After eating him and returning that number, well, that number just commutes with this vector. I can write it on the left. So now I have a complex number Z times the vector V. So what has this process given us? Well, it started with a vector X, and at the end, it ate that vector X and spat out some other vector ZV. But that's what a function does. A function eats a vector in H and spits out another vector in H. So at the very least, this object is a function from H to H. In fact, it's even a linear function, though. Why is it linear? Well, because what did X do? X got eaten by W, but W is an element of the dual space. So by definition, W is a linear map from H to C. So that means that this map from H to H, corresponding to this pair of objects, is a linear map and therefore an endomorphism. Okay. So formally,
we were allowed to do that. We were allowed to do that commutative thing because this is. What's the word? Associative thing because it's just matrix multiplication.
Well, this is just scalar multiplication. This is like
we were allowed to let the W latch on because it's just matrix multiplication, right?
If you like, yeah. I mean, you can interpret this as a matrix. I haven't yet defined what this object is. We were kind of saying, I mean, let me give a sort of caricature for what this does to motivate why it should be a linear map. But indeed, now that we have shown this is a linear map, you can actually interpret this as a matrix. So what I said, when I said W latches onto X, what's really happening is that this matrix is multiplying a vector.
Okay.
So it's less associativity and more kind of, you know, the semantics of the definition. But yeah, that's basically right. Okay, very good. So this process that I just described that takes in a V in H and a W in H dual and gives you a linear map is called the outer product. By contrast with the inner product is where I write these in the other way. If I wrote the other order, W with V, as we saw, this is an inner product, W with V, in math notation. So an inner product, for instance, takes two vectors, or if you like, a vector and a dual vector, and gives you a number. That's the inner product. The outer product takes a vector and a dual vector and gives you a linear map. So it's going the other way, if you like. It's going up in complexity. It gives you a matrix. So more precisely, the outer product is a map from the product H dual to end H, linear maps. Okay. That's what this is abstractly. Now let me show you again why this really nice Dirac-Brocket notation makes this obvious. So the way that I've written this as ket v bra w immediately suggests how you do this in a basis. So let's return to our previous convention, where ket v is a column vector, ket w is a row vector with conjugated entries. Now I just write them next to each other and again follow my instinct. So if I write them next to each other in the way I did on the previous slide, I have a column vector followed by a row vector, and now I follow the rules of matrix multiplication that I learned in kindergarten, right? So if I multiply a 2 by 1 vector by a 1 by 2 vector, I get a 2 by 2 matrix whose entries are v1, w1 star, v1, w2 star, blah, 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 blah. So again, the notation tells us how I take a column vector and a row vector and make a matrix, which is an element, again, of end H, just by following, you know, our instincts of matrix multiplication. Okay, so I like that notation. And of course, in general, you can write a general matrix. I mean, this is not special to 2 by 2, but I'm going to write out 2 by 2 because it's the simplest case. A 2 by 2 matrix with any entries can be written as a sum of outer products of these four basis guys. Or more generally, for Cn, I can write any operator O as a sum of components Oij times these outer product guys, Ei, Ej, where the E's are an orthonormal basis. So you will often see physicists and quantum computing people write operators like this in this outer product form. In particular, when we get to density matrices, you will often see a density matrix, which I have not yet defined, being written as a set of numbers pi times ket I bra I. So when someone sees a notation like this, you should think, oh, this is a sum of ket I bra I terms, which means this whole thing is a matrix, or if you like, an endomorphism, linear map. So when you see these things, you think matrix. Okay, very nice. We need another ingredient. So if O is a linear map, it's an element of the endomorphism ring on H. I claim, this is actually a pretty easy consequence of the Riesz representation theorem if you want an exercise, but I claim that you can show there exists a unique operator, O dagger. Remember, we used the symbol dagger before, but I'm defining a different notion of dagger that acts on operators now. There exists a unique operator, O dagger, with the property that the inner product between any element x in H and the output of the operator O on a second element y in H is the same as the inner product between O dagger, this other guy whose existence I'm claiming, O dagger acting on the left guy x, inner producted with the same y. So said differently, O and O dagger are related by the statement that in an inner product I can either act with O on the right or O dagger on the left. Now, if you've studied category theory, this might look formally similar to adjoint functors. The statement that two functors stand in adjunction is a statement that there are two Hom sets. There are two Hom sets, one in one category and one in a different category. And those two Hom sets are related by a particular isomorphism if in the one Hom set you act on the left guy with one functor, and in the second Hom set you act on the right guy with the adjoint functor. That looks a lot like this. I act on the left or on the right by two adjoint operators. And if you're curious, I'll drop this in the chat. this is not that interesting to me, but if you are extremely categorical and you want to ask, can this formal relationship between the Hilbert space adjoint and adjoint functors be made precise? The answer is kind of. If you're Bayes, you can say some categorical technobabble that really should be confined to NLab, where you categorify a Hilbert space to a 2 Hilbert space and try to make this Hilbert space adjoint a genuine adjunction of functors. I really don't care about this, but some of you probably do, so I will drop this here. Okay. All right. Good. So let me write what physicists write for this adjoint. Well, in Bra-Ket notation, how would we say this? This is the notation for taking a bra and evaluating it on the ket obtained by acting with the endomorphism O on Y. So I can put in parentheses, as Greg was alluding to, this is kind of associative, so I can first evaluate O on Y, and then the claim is that this is the same as some operator O dagger, where I take O dagger acting on X to get some element of H, I dagger it to get an element of H dual, and I evaluate that element of H dual on Y. So that's the claim. The claim is that you can either act with O on Y and then let X eat that guy, or you can find the bra dual to O dagger X and let that guy eat Y. And you'll get the same answer. A different way of saying this is that if I just look at the far left and the far right expressions in this equation, if I take bra X, O, ket Y, that's the same as taking the opposite order, bra Y, O dagger, ket X, and then daggering this thing. What does it mean to dagger a number, right? The output of the thing in parentheses is a number. This is a complex number, so I have to define what dagger means on a complex number, and for a number, we declare that Z dagger is just the complex conjugate. So you'll often see physicists write things like this, that daggering, you can flip the order of the Y and the X, and then dagger the operator. Okay. What does this mean in components? So again, we're focusing on finite dimensional Hilbert spaces. Let me first remind you let me restate essentially what I just said a moment ago. We are overloading the symbol dagger. What does overloading mean? The word overloading means we are defining a symbol to do different things in different contexts. What are those contexts? When the dagger acts on a bra or ket, I have defined it to give you the image of that object under the isomorphism between H and H dual. So ket v dagger is bra v dagger is ket v. But when acting on an operator, it's the Hermitian adjoint defined on the previous slide. So there's really 3 notions of dagger. When dagger acts on a bra or ket, it does this. When it acts on an operator, it does adjoint. And in the footnote, it says when acting on a complex number, it just does complex conjugation. That's what I mean by overloading. Why does this overloading make sense? Well, I claim that if we write an operator as a matrix in components, what dagger does is it transposes the matrix. So what does transposing a matrix mean? It means I flip all of the elements across the diagonal. So O10 in the bottom left goes to O10 in the top right, and vice versa. And then I conjugate all of the entries. So dagger is conjugation and flipping, transposing. Or to be more concise, this, O dagger ij is O conjugate ji. Transpose means you flip the 2 indices, I and j. So why does this overloading make sense? Well, as we saw a few slides ago, dagger on a bra or a ket, thought of as a 1 by n or n by 1 matrix, also flips the 2 indices I and j and conjugates each of the entries. So that's why these 2 apparently overloaded definitions are consistent. So in both cases, it acts in the same way on the components and indices. Or saying that differently, the 2 definitions are both compatible, as in they act in the same way if you interpret a bra or ket as a matrix, and they're consistent. What does consistent mean? Consistent means if I act with dagger on some combination of objects that defines a ket, that's the same as acting with my notion of dagger on each of the individual objects. So I act with with dagger on V, ket V turns into bra V. I act with dagger on O2, get O2 dagger, and act with dagger on O1 and get O1 dagger, but this reverses the order. So if you just remember that dagger reverses the order and then acts on each element in the string, you will always get a consistent result. That's much like the matrix transpose. If you've studied matrices or even the matrix inverse, the inverse of a product flips the order and so on. Okay. So the adjoint is, for us, not very scary. It's a particularly simple operation on matrices. Okay. Now, why is this Hermitian conjugate an interesting thing to study? Well, we first want to define a notion of a Hermitian operator. So we have the Hermitian adjoint, and now we say that an operator in endomorphisms of H is Hermitian if it's equal to its Hermitian adjoint. Right? So the term Hermitian adjoint refers to dagger. The term Hermitian operator refers to an operator that stays the same when you take its dagger. H dagger equals H. Okay, why is a Hermitian operator a nice thing? Well, it turns out that Hermitian operators have real eigenvalues. So let's recall, what is an eigenvalue? A non-zero vector V is said to be an eigenvector of some operator or matrix H with associated eigenvalue lambda if the operator H acts on the vector V and it returns a scalar multiple, a number lambda times the vector V. Right? In general, this will not be true. You act with an operator on a vector, it messes it up, it rotates it, it does some horrible thing. But for certain special vectors, you hit the vector with the operator and you get a scale multiple of the vector back. That's an eigenvector with associated eigenvalue. Okay, let me prove in 2 lines for you that with that definition of eigenvector, eigenvalue, a Hermitian operator has real eigenvalues. Okay, here's the proof. Assume H dagger equals H, so it's Hermitian. Now stare at the following. Stare at the expression inner product V with HV. By definition of adjoint, I can either act on the right with H or on the left with H dagger. So let me act on the left with H dagger. I do that, but then I remember H dagger equals H. That means I can replace H dagger with H. So that means these 2 things on the left and right are equal. On the other hand, we've assumed H on V is lambda on V. Lambda times V. It's a number. Number times V. So I will replace on the left and right HV with lambda V. So that means inner product V with lambda V is inner product of lambda V with V. This might look trivial to you, but this is not trivial. We must remember, way back from our definition of Hilbert space, right? This thing is not symmetric when I flip the order, right? The guy in the first slot, if you multiply by a number, it comes out as the conjugate. The guy in the second slot, if you multiply by a number, it comes out as the number not conjugated. So scalar multiplication in the 2 slots are different, right? So with that in mind, going back to the proof, when I pull out the lambda on the left side of the equation, but on the right side of the inner product, when I pull out this lambda, it comes out as lambda. On this side, when I pull out the lambda, well, he's in the left, so he comes out as lambda star. So that means lambda times the norm squared of V equals lambda star times the norm squared of V, and by assumption, V is non-zero, so I can divide. And that means lambda is lambda star, so lambda is real. Great, Hermitian operators have real eigenvalues. We're in business. I'll also state a version of the spectral theorem. You may have heard of the spectral theorem. There's a weaker notion, weaker than Hermitian, called normal. An operator is normal if it commutes with its adjoint. That means A times A dagger is A dagger times A. Clearly, a Hermitian operator is normal because in that case, both sides of this equation are just A squared. If A equals A dagger, then A dagger is A dagger times A, and both of them are A squared. All Hermitian operators are normal, not all normal operators are Hermitian. There's a theorem which I will not prove for you again, but an operator is normal if and only if it admits a representation of this form. So remember, when we write these inner products, you're thinking matrix. So this is a matrix where it's written as a linear combination of numbers lambda I, which are the eigenvalues of A, and outer products V with V, where VI is an orthonormal basis of Cn. So what does that mean? Well, that means if I write this operator in the VI basis, it is diagonal. So that V1 up to Vn, V1 up to Vn. In that basis, this matrix is diagonal. All other entries are 0. So said differently, a matrix is normal if and only if there exists an orthonormal basis of Cn with the property that the operator is diagonal in that basis. And since all Hermitian operators are normal, every Hermitian operator can be diagonalized in this way.
You're probably going to answer this again, but since you've introduced Hermitian operators, like, why do we care about those specifically? Why is this a nice property to have physically?
Oh, very good. Yes. So indeed, the reason it's nice has to do with this reality condition, the real eigenvalues. So, in fact, that's actually the next slide. The reason this is nice physically is that if I go out into the real world and measure something, I measure the angle at which some electron is deflected in an experiment. Some quantity I measure in the real world will be a real number. So the fact that, as we saw in the previous slide, that the eigenvalues of a Hermitian operator are always real means that there's at least a chance that eigenvalues of Hermitian operators could be models for observable quantities because they're guaranteed to be real. So that's the answer to the question. I mean, real numbers are what we measure, and eigenvalues of Hermitian operators are real. So that's what ends up being nice. But okay, before jumping ahead, I guess I should stop and see if there's other questions or follow-ups on that question.
I have a question. So what does the dagger do again? I kind of forgot. The dagger.
What does the dagger do? Yeah, I mean, if you think of this as a matrix, like, here's an explicit example. 0, I, 1 plus I, 0, for instance, or even 1, I don't know. Here's a matrix. What does dagger do? Well, I do two things. I first flip the entries in the top right and bottom left. So I flip these guys. So that gives me 0, 1 plus I, 1. And then I do a second thing, which is everywhere I see the number I put a minus sign in front of it. So this is now minus I and 1 minus I. So that's what dagger does. Flips and replaces I with minus I.
Oh, thank you. Useful.
Good. Other questions? Holo is reaching peak horniness. I don't know if that's a good thing or a bad thing. Okay, good. All right, so to answer, well, in slightly more detail, Greg's question. So we were saying Hermitian operators have real eigenvalues, which is good, since we measure real numbers. So now I'm ready to state for you a collection of facts. These are sometimes called postulates of quantum mechanics. I hate that term. I'm not postulating anything. These are just facts about reality. So, I mean, like it or lump it. These are not things I'm assuming. These are true. Okay, so here are things that are true. These are facts. First, we already said the state of a physical system is a ray in Hilbert space. Okay, we said that a couple acts ago, one act ago or something. Next fact, every observable, everything you can go out and measure in the lab in a quantum system, A, is associated with a corresponding Hermitian operator, which I write with A as a hat. So here I'm just distinguishing between A is the thing I observe, like energy. A hat is the corresponding operator that represents that observable. Okay, that's a fact. Another fact, if I go out and measure the observable A, like energy, the only possible values I will ever get for that measurement are the eigenvalues of A hat. That's it. I can get no other number, only the eigenvalues of that operator. Well, that's good, because that guarantees the only result I get in a measurement is a real number, which is nice. But now you ask, what determines which of the eigenvalues I get in a measurement? Okay, well, the answer is, if your state, your quantum state, is described by a ket psi, well, we recall that from the previous slide with the spectral theorem, an operator, well, all Hermitian operators are normal, and as normal operators, A admits a representation of this form, which in particular means that its eigenvectors are an orthonormal basis of Cn. So if its eigenvectors are an orthonormal basis, that means I can take any vector I like and write it as a linear combination of basis vectors, where those basis vectors are eigenvectors of A. So I can do that for any state at all, write it as a sum of eigenvectors of the operator a hat, and then the probability that you measure eigenvalue lambda I will be proportional to the norm squared of the number appearing in that expansion. So you expand your state in eigenvectors, look at the numbers in that expansion, and the norm squareds of those numbers in the expansion are the probabilities. I mean, to be more precise, if this was not normalized, the probability of getting, say, lambda 1 would be a1 mod squared divided by the sum of all of the mod squareds. I have to divide by this to ensure that adding all the probabilities will give me 1, because they have to sum to 1 because I get something. But this is why I said before we often assume that the state is normalized, which means this is equal to 1. If we make that assumption, I can drop the bottom, and then it's just this. Final fact, fact 5. If I perform a measurement associated with observable A, immediately after that measurement, which has output some value lambda I, the state of the system is now changed. If the state was psi before the measurement, and I perform the measurement and get lambda I, then after the measurement, the state of the system is now in this new state Vi, where Vi is the eigenvector of the operator A with the same eigenvalue as the thing I measured. So I measure it, it changes the state to the eigenvector associated with the output of my measurement. Okay. These are the facts of life. Good question.
Sorry, I was at the start of this slide. I think I was busy getting angry at Hollow, so I might have missed it if you said so. But was there like an explicit way of thinking about this a hat, or is this just a Hermitian operator that we kind of know exists?
Yeah, I mean, for each observable on a case-by-case basis, you have to find out what a hat is. There's no procedure that says, oh, take A with the word associated for A, like energy, and map that word onto an operator. We don't know how to do that. You have to go into the lab and figure out what the operator is. And I'll show you some examples for specific things where we can write down the operators. But yeah, there's no specific relation between the observable and the operator. You just have to figure it out.
Okay.
Good. Other questions? I think that's basically the end. Oh, no, there's a little bit more. There's 2 more slides, but it's almost the end of this act. So other conceptual questions. This is kind of the meat. I mean, if you understand these facts, then you've already understood most of an undergraduate quantum mechanics course, so that's great. But I do have more, so if there's questions, ask them, and otherwise I'll forge on. Okay, forging on then.
I have one. So what is this basically used for? I kind of did not understand that.
Yeah, good. So oh, sorry. Go ahead.
Like, what is this used for? I mean it like that.
Yeah, so I will, in Act 3, I'll show you a very concrete experiment where you can use this to understand the results. But just to preview that for a moment, you could imagine, suppose you have an electron. Electrons have certain properties associated with their spin. So for instance, they can be spin up or spin down, as we saw in the beginning. And I can write down an explicit operator for the electron spin in some direction. So for instance, its spin along the x-axis will be associated with this operator. So the usefulness of this is that if I hand you an electron and you put it in a magnetic field so that it's spinning up, and then I say, I'm going to go measure this electron spin along the x-axis, not along up-down, which is z, but along some other axis x. Then applying these rules will give you the exact probabilities that you will measure the spin of the electron as being left versus right along the x-axis. For example, that's one case where you can use this. It will tell you exact probabilities for your measurements of things associated with electrons.
So it's not always 50-50 probability?
No, it's not. I mean, in the case I just said, it will be. If it's spin up, you will get 50-50 left and right. But more generally, it does not need to be 50-50. You can have different probabilities that depend on these eigenvalues. It can be skewed. It can be 90%, 10%. It can be anything.
Oh, that is interesting. Thank you.
Yeah. Other questions? All right. Then to finish this act, this is kind of a targeted comment for the Greg project, but in preparing these slides, I realized I was confused about some of the notation in Tom's paper. So when I write, and by extension when Tom writes, mathcal A of H, let me define this for you. Mathcal A of H is the operator algebra on H. So let me explain what an operator algebra is. So first, what is an algebra in general? Well, in math, an algebra A over the complex numbers is essentially a vector space over the complex numbers where you know how to multiply the vectors. What does that mean? It's a vector space over the complex numbers, and given two vectors, I can multiply them to get another vector in the space. Now, this is not like the cross product or something where you take two vectors and get a third vector. This is different. This is, for instance, in 2 dimensions, you can think of the complex numbers as being an algebra, where I can take two complex numbers that we think of as vectors in the plane, but I can multiply them to get another vector in the plane. For example, that's an algebra. Okay. Now I want to convince you that the space of linear operators, the endomorphisms on H that we discussed, has an algebra structure. It is, in fact, an endomorphism algebra. Why is that? Well, to be an algebra, I first have to be a vector space. So I know how to add operators. I add the matrices, for instance, component-wise, and I know how to multiply them by a number. To multiply a matrix by a number, I just multiply each component. So it's definitely a vector space. I can add and scalar multiply. But I need to be able to multiply the vectors as well. So how do I multiply two operators on my Hilbert space? Well, by definition, an operator is a map from H to H. So I will define multiplication of these two objects as the composition of the two functions. So, right, given two functions with the same domain and codomain, I can compose them to get a new function, and that is also an endomorphism. So that is my definition of the multiplication. It's just composition. So now I've given you all the properties. I know how to scalar multiply, add them, and multiply them, so that makes it an algebra. So the endomorphisms on H are an algebra, which I call the operator algebra. The comment for Greg is that I was confused. I thought A of H was the algebra of observables, which is different. So the algebra of observables is a different algebra where the underlying set is the collection of Hermitian operators, A dagger equals A, which Tom writes as A SA for self-adjoint. But that is not the same as the operator algebra. So, for example, Hermitian operators, this set is not even closed with respect to this product. If I take a product of two Hermitian operators, H1, H2, dagger, that's H2 dagger, H1 dagger, which need not be the same as H1, H2. Why? Because these are Hermitian, so the dagger does nothing. But the top is H2, H1. And multiplication of operators or matrices does not commute, right? So H2, H1 is not necessarily the same as H1, H2. So the algebra of observables is not a closed algebra with the product defined by composition. I thought that's what he was talking about. That's not what he's talking about. To make the algebra of observables, there's a more complicated process where you define the product slightly differently. You define H1, I'll write the product like this to emphasize it's a new symbol. H1 O dot H2, you define as a half the symmetrized composition, H1 H2 plus H2 H1. This gets rid of the fact that this thing doesn't commute, because I do it in both orders and average. So an algebra of operators with this product satisfying certain properties is a well-known structure called a Jordan C-star algebra. So I thought when Tom writes A of H, he meant the Jordan C-star algebra associated with Hermitian observables and this product. That's not what he means. He means a much simpler thing. He means this operator algebra, A of H, with the usual product and including non-Hermitian operators. So all operators, that's it.
You mentioned in the footnote that this is a Jordan C-star algebra. Do you happen to know if the operator algebra is also a C-star algebra?
It is, yeah. It's not a Jordan C-star algebra, but it is a C-star algebra. I mean, for those that don't know, essentially a C-star algebra, I'm going to write a very funny equation. C-star algebra equals algebra plus dagger. So a C-star algebra is just an algebra along with an operation called dagger that has the properties of the dagger I already told you about, right? So you can dagger an operator and it acts as Hermitian adjoint. So mathematicians like to abstract away that structure, and they say, I'm not going to think about the specific dagger you just showed me. I'm going to think about some more general dagger that satisfies a list of axioms. And an algebra along with that operation dagger that satisfies those axioms is called a C-star algebra. So the operator algebra is a C-star algebra because we know how to take a dagger. It just so happens that operators in the operator algebra are not fixed points of the dagger operation, right? You don't dagger a general operator and get the same thing back. But elements of the algebra of observables, ASA, elements of this guy are fixed points of the daggering operation. You dagger them and get the same thing back because they're Hermitian. So that's the difference. They're both C-star algebras, but one is fixed. I mean, the dagger acts trivially on elements of the Hermitian operators, right?
Okay.
Good. Other questions? Okay. Well, I'm almost done with this section. The last section will be somewhat faster because it's just for fun, essentially. But again, in the spirit of kind of reassuring you that this is not that complicated. I mean, I said a lot of fancy words like out C-star algebra and all of this blah, blah, blah. I want to convince you that the algebra I'm talking about when H is Cn is not complicated. So again, let's find what is the operator algebra on the Hilbert space H is Cn. Well, remember the notation you typically use when you learn abstract algebra is that mat sub n of C is the algebra of n by n matrices with entries in C. It's an algebra. Remember, an algebra is a vector space, and I can multiply the vectors. So why are matrices a vector space? Well, as I already alluded to, I can scalar multiply a number times a matrix. I just multiply every entry. So that becomes 2 times 1, 2 times 0, blah, blah, blah. I can add them just by adding the entries. So matrices form a vector space, and I know how to multiply the vectors, right? I can multiply two matrices in the usual way with the rules you learned in kindergarten. So that means matrices form an algebra. And I claim, it hopefully is obvious now, that the algebra, the operator algebra for the Hilbert space Cn is simply the matrix algebra mat sub n of C. So it's an algebra you already know. It's an algebra literally that you learn in high school algebra. You don't call it an associative algebra over the complex numbers, but it's something you study. So there's nothing fancy about that. Okay, that's the end of that act. And then the last one is just for fun. This will be faster. I know I've gone for about an hour 45, so this will be a quick fun example to ease up at the end, and then we'll be done. But before I do that, let me stop the recording and see if there's questions on this stuff.